Welcome to this presentation on inference for regression. In this session, we will be focusing specifically on section 14.3, which is about predicting values and estimating means using linear models. This is an important concept in statistics, especially when we want to make informed predictions based on data we've collected. Imagine you're out fishing at a lake, like the person in the photo on this slide. Perhaps you're interested in understanding the relationship between the acidity of the water in the lake and the amount of mercury found in the fish you catch. You've collected data, and now you want to make predictions. This is where prediction intervals and confidence intervals come into play. Throughout this section, we'll explore how we can use these statistical tools to answer different types of questions. Specifically, we'll see how prediction intervals can help us estimate the mercury level for an individual fish, and how confidence intervals allow us to make statements about the average mercury level in all fish in the lake. We'll also discuss the nuances of these intervals, such as why a prediction interval is typically wider than a confidence interval. This is because predicting the value for an individual fish involves more uncertainty than predicting the average for all the fish in the lake. By the end of this section, you should feel more confident in your ability to use linear models to predict outcomes and estimate means, whether you're studying fish, analyzing trends in business, or working with any other type of data. Let's dive in and explore these concepts in more detail. When we work with a regression line, there are essentially two types of questions we can ask. Understanding these questions is crucial because the type of question dictates the kind of answer we can expect and the level of uncertainty involved. The first type of question we might ask is about an isolated individual. For example, suppose we're trying to predict a specific outcome for one single fish in our lake based on the data we've collected. We might want to know, what is the predicted mercury level for this particular fish? This kind of question focuses on making a prediction for a single entity using the regression line. The second type of question shifts our focus from an individual to a group of individuals. Instead of asking about one fish, we might ask, what is the average mercury level for all the fish in the lake, given the pH level of the water? Here, we're concerned with estimating the mean value for a larger group, which often involves less uncertainty than predicting an individual outcome. It's important to note that our uncertainty in answering these questions varies. Predicting an outcome for an individual tends to involve more uncertainty because individuals can vary widely from the average. On the other hand, when we estimate the mean value for a group, our prediction usually involves less uncertainty because we are averaging out those individual variations. In summary, the nature of the question, whether it's about an individual or a group, determines both the method we use and the level of uncertainty we should expect in our answer. As we move forward, we'll see how these concepts play out in more detailed examples. Let's consider a concrete example to better understand how we use regression lines in practice. Here, we're looking at data collected on the amount of mercury found in largemouth bass from a specific lake. This data is displayed in the scatter plot on this slide, where each point represents an observation, with pH levels of the lake water plotted on the x-axis and the corresponding mercury levels in the fish plotted on the y-axis. To make sense of this data, we've calculated the equation of the regression line, which is shown here as predicted mercury level equals 1.53 minus 0.152 pH torr. This equation helps us understand the relationship between the acidity of the water, measured by pH, and the mercury levels in the fish. The slope of the line, minus 0.152, indicates that for each 1 unit increase in pH, we expect the mercury level in the fish to decrease by 0.152 micrograms per gram, on average. The intercept of 1.53 suggests that when the pH is 0, the predicted mercury level would start at 1.53 micrograms per gram, although, in practical terms, a pH of 0 would be far outside the range of our data. This regression line provides a useful tool for making predictions. For example, if the pH level of the lake were measured at 7, we could plug that value into our equation to predict the corresponding mercury level in the fish. By doing so, we start to see how regression can help us answer both of the types of questions we discussed earlier. about individual fish, and about the average mercury level across multiple fish. The visual representation provided by the scatter plot and regression line also helps to quickly assess how well the line fits the data. In this case, the points are somewhat scattered around the line, suggesting that while there is a general downward trend, there's also considerable variability in the data, which might influence the certainty of our predictions. This example sets the stage for understanding the distinction between prediction intervals and confidence intervals, which we'll explore in the upcoming slides. These intervals will help us quantify the uncertainty in our predictions, whether we're interested in individual fish or the average across a group. Now that we've introduced the concept of using a regression line to make predictions, let's delve deeper into the kinds of questions we can answer with this approach. On this slide, we see two specific questions that we might ask based on our regression analysis of mercury levels in fish. First question: if the acidity of a lake measures pH 7, what is the mean level of mercury found in all the fish in the lake? This question is asking us to estimate the average mercury level for a group of fish when the lake's pH level is 7. This is a question about the mean, which means we're focusing on the overall trend in the data rather than individual cases. The answer to this question would typically involve calculating the mean mercury level for all fish when the pH is 7, using the regression line equation. Second question: a fish is caught with a pH of 7. What mercury level should we predict this fish will have? Here, the focus shifts from the group to an individual fish. We're asked to predict the mercury level for this specific fish, given that the pH of the water it was caught in is 7. This type of question requires us to use the same regression line, but now we're making a prediction for one individual fish, which involves more uncertainty than estimating the mean for a group. The difference between these two questions is subtle but important. The first question deals with an average value, which tends to be more stable and less variable. The second question deals with an individual prediction, which is more prone to variation and uncertainty. As we proceed, we'll see how these different types of questions influence the statistical tools we use, such as confidence intervals for the first question and prediction intervals for the second. Understanding these differences will help you make more accurate and informed predictions when working with data. Both of the questions we just discussed can be answered using the regression line equation that we derived earlier. Let's go through how we would use this equation to provide answers to these questions. The equation we have is predicted mercury level 1.53 minus 0.152 minus pH is 4. For the specific case where the pH is 7, we can substitute 7 into the equation to predict the mercury level. Predicted mercury level 1.5.152 times 7 just works. When we carry out this calculation, predicted mercury level 1.53 minus 1.064 equals 0.466. So, whether we're predicting the mean mercury level for all fish in the lake at a pH of 7 or predicting the mercury level for an individual fish caught at that pH, the predicted value is 0.466 micrograms per gram. However, it's crucial to remember that these two predictions carry different levels of uncertainty. For question 2, where we're predicting the mercury level for an individual fish, the uncertainty is greater. This is because individual fish can vary more than the mean of a group of fish. On the other hand, question 1, which asks about the average mercury level in all fish in the lake, involves less uncertainty because we are dealing with a group average, which tends to be more stable. This difference in uncertainty is why we use different intervals, prediction intervals for individual predictions, and confidence intervals for group means. As we move forward, we'll see exactly how these intervals work and why understanding the distinction is important for making accurate and meaningful predictions. To properly quantify the uncertainty in our predictions, we use specific statistical tools depending on the type of question we're answering. When we're concerned with estimating the mean value for a group, such as in question 1, where we asked about the average mercury level in all fish at a given pH level, we use confidence intervals. Confidence intervals give us a range within which we expect the true mean of the population to lie, with a certain level of confidence, typically 95%. On the other hand, when our focus shifts to making predictions about individuals, as in question 2, where we predicted the mercury level for a single fish caught in water with a pH of 7, we use a prediction interval. A prediction interval provides a range within which we expect the actual value for an individual observation to fall. It's important to note that prediction intervals are generally wider than confidence intervals. This is because there is more variability when predicting a single outcome than when estimating a group mean. In other words, individual outcomes tend to deviate more from the regression line compared to the average of a group, hence the greater uncertainty reflected in a wider interval. As we continue, we will explore examples of how to calculate and interpret these intervals so you can effectively express and understand the uncertainty associated with both group means and individual predictions. Prediction intervals are a powerful tool when our goal is to make predictions about individual outcomes rather than estimating a population parameter. Unlike confidence intervals, which are designed to give us a range within which we expect the true mean of a population to fall, prediction intervals are all about individuals. When we use a prediction interval, we're asking a very different kind of question. We're no longer concerned with the average value for a group, but instead, we want to predict where an individual observation is likely to fall within a given range. This could be, for example, predicting the mercury level in a specific fish caught in our lake, given the pH level of the water. Since individual outcomes tend to show more variability than group averages, prediction intervals must account for this additional uncertainty. This is why prediction intervals are generally wider than confidence intervals. They need to encompass the greater variability that comes with individual predictions. As we proceed, we'll discuss how to calculate these intervals and interpret them in the context of real-world examples. Understanding prediction intervals is crucial for making accurate individual predictions. Whether you're dealing with fish in a lake, sales projections, or any other situation where individual outcomes matter, prediction intervals are intentionally wider than confidence intervals, and there's a very good reason for this. When we're making predictions about individual values, like the mercury level in a single fish, there's naturally more uncertainty involved. This increased uncertainty comes from the fact that individual outcomes can vary significantly from one another. While the mean of a group tends to be stable, individual observations might be influenced by many small factors that introduce variability. Therefore, prediction intervals need to account for this by being broader. In contrast, when we use a confidence interval, we're trying to estimate the mean of an entire group. Since we're averaging out the individual variations, the result is a more stable and predictable value, which allows the confidence interval to be narrower. To summarize, the reason prediction intervals are wider is because they reflect the additional uncertainty and variability inherent in predicting individual values, as opposed to the more predictable nature of group means. This distinction is crucial for making accurate predictions and interpreting the results correctly in any statistical analysis. Let's take a closer look at an example to understand the practical application of confidence intervals and prediction intervals in a real-world scenario. This example continues our analysis of mercury levels in fish, but now we're applying these concepts to make meaningful statistical inferences. Here, we see two types of intervals based on our regression analysis. 1. 95% confidence interval for the mean mercury content. The 95% confidence interval for the mean mercury content of fish caught in the lake is given as 0.383, 0.546. This interval tells us that we are 95% confident that the true mean mercury level for all fish in the lake falls within this range. Notice that this interval is relatively narrow. This narrowness reflects that when we are estimating the average mercury level for a large number of fish, there is less variability, and therefore we can be more precise in our estimation. 2. 95% prediction interval for the mercury content of an individual fish. The 95% prediction interval for the mercury content of an individual fish is given as 90.106, 1.036. This interval is much wider than the confidence interval, which aligns with what we discussed earlier. There is more uncertainty when predicting individual outcomes. A notable issue with this prediction interval is that it includes negative values, which are impossible for mercury levels. This suggests that there is a lot of variability in the data, which makes the prediction less reliable. The wide interval indicates that the data might be too noisy or variable to make a useful prediction for an individual fish. This example illustrates the importance of considering the context and the type of prediction you're making when interpreting statistical intervals. While the confidence interval gives a reasonably precise estimate of the average mercury content in fish, the prediction interval highlights the challenges and limitations when making predictions about individual fish due to greater variability. As we proceed, we will discuss strategies to address such variability and how to interpret these intervals in the context of your specific data and research questions. Let's move on to a new example that will help us distinguish between when to use a confidence interval, CI, and when to use a prediction interval, PI. Imagine a consumer group that is investigating the accuracy of calorie counts advertised on frozen dinners. They compare the advertised calorie content with the actual calorie content based on laboratory testing. According to the regression analysis, the group finds that a frozen dinner advertised to have 1,000 calories actually has, on average, 1,100 calories. Given this scenario, we can ask two different questions. 1. For all frozen dinners, what is the mean caloric content if the advertised content is 1,000 calories? This question is asking about the average or mean calorie content across all frozen dinners that advertise 1,000 calories. Since this is a question about a group mean, it can be answered using a confidence interval. The confidence interval will give us a range where we expect the true mean calorie content for these dinners to lie. 2. The Frozen Man TV dinner advertises that it has 1,000 calories. What is the actual calorie content of one dinner? This question, on the other hand, is focused on predicting the calorie content of a single frozen dinner, specifically the Frozen Man TV dinner. To answer this, we would use a prediction interval. The prediction interval will give us a range within which we expect the actual calorie content of that single dinner to fall, accounting for the greater variability in individual outcomes. In summary, the first question deals with a population parameter, the mean calorie content for all similar dinners, which makes a confidence interval appropriate. The second question deals with predicting a specific individual outcome, the calorie content of one particular dinner, which requires a prediction interval due to the additional uncertainty involved. As we continue, we'll explore the specifics of how to calculate and interpret both confidence intervals and prediction intervals in situations like this, ensuring that we use the right tool for the right type of question. To summarize the distinction between when to use a confidence interval, CI, versus a prediction interval, PI, let's revisit the two questions from the previous slide and provide clear answers. 1. For all frozen dinners, what is the mean caloric content if the advertised content is 1,000 calories? This question is about estimating the mean caloric content for a large group of frozen dinners. Because it focuses on the average, it can be answered using a confidence interval. The confidence interval provides a range in which we expect the true mean calorie content to fall, considering all frozen dinners that advertise 1,000 calories. 2. The Frozen Man TV dinner advertises that it has 1,000 calories. What is the actual calorie content of one dinner? This question is concerned with predicting the calorie content of a single frozen dinner, specifically one TV dinner. Since we're predicting the outcome for an individual product, we use a prediction interval. The prediction interval gives a range within which the actual calorie content of this specific dinner is likely to fall. Understanding the difference between these two intervals helps ensure that you apply the correct statistical method depending on whether you're interested in a group average or an individual prediction. As we've seen, confidence intervals are used for estimating population parameters like the mean, while prediction intervals are used when making predictions about individual outcomes. When performing regression analysis, it's important to remember that certain conditions must be met for the results to be valid. One of the key conditions is linearity, the assumption that the relationship between the predictor variable and the outcome variable is a straight line. But what happens if this condition is not satisfied? Let's explore the potential issues that can arise. Number 1. Estimates of slope and intercept may be biased. If the true relationship between the variables is not linear, but we apply a linear model, the estimates of the slope and intercept might be incorrect or biased. This means that the coefficients we calculate won't accurately represent the true relationship, leading us to draw incorrect conclusions from the data. 2. Predicted values and estimated means will be biased. Along with biased estimates, the predicted values we generate using the regression model will also be biased. If the model doesn't correctly represent the data, our predictions will be systematically off. Similarly, the estimated means of the outcome variable, based on our model, won't reflect the true means in the population. 3. Confidence intervals and prediction intervals are not reliable. Since both confidence intervals and prediction intervals are based on the assumption that our model is correctly specified, if the linearity condition is not met, these intervals will be unreliable. They might be too narrow or too wide, or they might not capture the true values as they're supposed to. 4. A transformation may be able to straighten up a nonlinear trend. Fortunately, there are ways to address nonlinearity. One common approach is to apply a transformation to the data. For example, taking the logarithm of the predictor variable or the outcome variable, or both, might help to straighten out a nonlinear relationship. By transforming the data, we can often get closer to satisfying the linearity condition and thereby obtain more reliable estimates and predictions. In summary, ensuring that the linearity condition is met is crucial for the accuracy and reliability of regression analysis. If it's not met, we risk generating biased results and misleading conclusions. However, transformations offer a powerful tool for dealing with nonlinear data, allowing us to apply linear models more effectively. Another condition that is important in regression analysis is the normality of errors. Let's explore what can go wrong if this condition isn't met. Estimates remain unbiased if other conditions hold. Even if the errors, the differences between the observed and predicted values, are not normally distributed, as long as other key conditions, such as linearity and independence, are met, the estimates of the slope and intercept of the regression line, as well as the predicted values of the outcome variable y for a given x, will still be unbiased. This means that, on average, the estimates will be correct. P-values for hypothesis tests will be approximately correct. The p-values obtained from hypothesis tests on the slope and intercept will still be reasonably accurate. This means that even with non-normal errors, we can still conduct hypothesis tests on our regression coefficients with some confidence that the results are valid, assuming other conditions hold. Prediction intervals may not be accurate. One of the more significant consequences of non-normal errors is that prediction intervals may not be accurate. Since prediction intervals are designed to capture the variability in individual predictions, if the errors are not normally distributed, the intervals may be too narrow or too wide, and therefore not provide a reliable estimate of where individual predictions are likely to fall. In summary, while non-normal errors don't necessarily bias the estimates of the regression coefficients or severely impact hypothesis testing, they do affect the accuracy of prediction intervals. This is why checking the distribution of errors is an important part of validating your regression model, particularly when you need to make predictions about individual outcomes. Another potential issue that can arise in regression analysis occurs when the standard deviation is not the same for all values of x star, a condition known as heteroscedasticity. Let's break down what can go wrong in this situation. 1. Unbiased estimates. Even if the standard deviation of the errors is not constant across all levels of x, the estimates of the slope, intercept, means, and predicted values will still be unbiased. This means that, on average, these estimates are correct, and there is no systematic overestimation or underestimation. 2. Inaccurate confidence intervals, prediction intervals, and p-values. The real problem with heteroscedasticity is that it leads to inaccurate confidence intervals, prediction intervals, and p-values. Since these intervals and p-values are calculated based on the assumption of constant variance, homoscedasticity, heteroscedasticity can make them too narrow or too wide, thus not accurately reflecting the true uncertainty in the estimates. 3. Transformations as a possible solution. One common approach to dealing with heteroscedasticity is to apply a transformation to the data, such as taking the logarithm or square root of the outcome variable. Sometimes these transformations can even out the variability across different levels of x, helping to meet the assumption of constant variance. However, transformations are not always effective, and they may not fully resolve the issue in every case. In summary, while heteroscedasticity doesn't bias the point estimates of your regression model, it does impact the reliability of the intervals and hypothesis tests derived from the model. If you suspect heteroscedasticity, it's important to consider transformations or other techniques to ensure that your intervals and p-values are accurate and meaningful. Another critical assumption in regression analysis is the independence of errors. Let's examine what can go wrong when this condition is violated. 1. Inappropriate regression model. If the errors are not independent of each other, the regression model you're using may not be appropriate. Independence of errors means that the value of one error term should not be influenced by the value of another. When errors are dependent, it often indicates that there is some underlying pattern or structure in the data that the model is not accounting for, which can lead to inaccurate estimates and predictions. 2. Common scenario, time series data. A typical situation where errors may not be independent is when working with time series data. In time series data, the predictor variable is time, and it's common for observations to be correlated with each other across time. For example, the value of an error term today might be related to the value of an error term yesterday, which violates the independence assumption. In such cases, special models like autoregressive integrated moving average, ARIMA, or other time series models are often more appropriate than standard linear regression, as they account for the dependence between observations. In summary, the independence of errors is a key assumption for the validity of a regression model. When errors are not independent, especially in cases like time series data, the model can produce misleading results. Recognizing when this assumption is violated and adjusting your approach accordingly by using more appropriate models is crucial for accurate analysis. Another important consideration in regression analysis is the impact of influential points, data points that have a disproportionate effect on the regression model. Let's explore how these points can affect your analysis. 1. Influence of outliers. Regression models can be greatly influenced by outliers, especially when these outliers are far from the bulk of the data. An outlier is a data point that significantly deviates from the other observations. If not properly identified and addressed, outliers can skew the results of the regression model, leading to inaccurate estimates of the relationship between variables. 2. Effect of outliers at the extremes. Outliers that occur at the extremes of the x variable's distribution are particularly problematic. These points can have a strong effect on the estimated slope of the regression line. For example, an outlier with a very low or very high x dot value can pull the slope of the line up or down, creating a misleading representation of the overall trend in the data. It's crucial to be cautious of these extreme values and to consider whether they represent real variation in the data or are simply anomalies that could distort the analysis. In summary, influential points, particularly outliers at the extremes, can have a significant impact on your regression model, potentially leading to incorrect conclusions. It's important to identify these points, assess their influence, and decide whether they should be included in the analysis or addressed through methods like robust regression, which is less sensitive to outliers. The final potential issue to consider in regression analysis is the interpretation of R², the coefficient of determination. Let's explore what can go wrong if R2 is misinterpreted or used without proper context. 1. Understanding. R2 is a measure of goodness of fit that tells us how well our regression model explains the variability in the outcome variable. Essentially, R indicates the proportion of the variance in the dependent variable that is predictable from the independent variables. For example, an r-squared value of 0.8 means that 80% of the variance in the outcome variable can be explained by the model. Importance of the linearity condition. Before we interpret the R2 value, it's crucial to ensure that the linearity condition for the regression model is satisfied. The R2 value assumes that the relationship between the variables is linear, so if this assumption is not met, the R2 value may be misleading. A high R-scored in a nonlinear relationship might falsely suggest that the model is a good fit, even though a linear model is not appropriate. Checking model conditions first. It's essential to check that all the necessary conditions for a linear regression model are satisfied, such as linearity, independence of errors, constant variance, homoscedasticity, and normality of errors, before considering the R-squared value. Only after verifying these conditions can you confidently interpret R-squared as a meaningful measure of how well your model fits the data. In summary, while R-squared is a useful statistic for understanding the fit of a regression model, it must be interpreted in the context of a properly specified model. Misinterpretation of R-squared can lead to overconfidence in a model that might not actually be appropriate for the data. Therefore, always verify that the linear regression assumptions are met before relying on R-squared to assess model performance.